Hi, good morning. So I'm Akash and I'm an AI researcher at WISP. So let me begin by introducing Elena. She is a PhD student in the Netherlands and recently, a few months ago, she reached out to us with a very interesting problem. So Elena has a speech disorder. At a very young age, her vocal cords were removed because of throat cancer, because there was a tumor found in her throat. And because of which, whenever she speaks, she produces only whispered sounds or some sort of whistling sounds. So we had her record an audio sample for us. Let me play that for you first. So as you heard, this is really high pitched and it does not have that characteristic pitch like what I'm talking. And this is generally considered as non-standard speech. So our first idea was let's use speech to text AI models. So when Elena makes a presentation, we can display whatever she is talking and the people in the audience can understand her. So we picked up like a lot of state-of-the-art models, large speech models, and as you can see on the text, all the models get it really wrong. And in the case of Whisper, which is trained on literally thousands, hundreds of thousands of hours of data, it predicts completely different. So then we thought, okay, when Elena is making her presentation, we can reduce the background noise and enhance her speech. And this is where speech enhancement models come in. On the slide, you see a spectrogram of the audio that you just heard. For those of you who don't know what a spectrogram is, it's a representation of audio with x-axis showing the time and y-axis showing the frequency. So at any given point of time, spectrogram shows the energies at different frequencies. And this is what you get when you use one of the state-of-the-art models. I've depicted some yellow boxes, and what you can see is most of Elena's speech is considered as noise. Now, this is a problem. In fact, we tried a lot of speech models, and the results were very similar. It works for me, but it does not work for Elena. And she's not alone. So worldwide, there are roughly 300 million people who suffer from some sort of voice disorder. They've lost their voice because of a disease, or they stutter. This includes people with throat cancer, people with diseases such as Parkinson's, etc. And the problem is, they can't exactly say what they want when they want to. Our lives are getting more and more digital, and because of this, there is a very big prevalence of voice interfaces. This means a lot of speech models are already being used in applications. This includes speech-to-text models used in voice assistants, speech enhancement models used in phone calls and video calls to improve the quality of audio, etc. And these models are not accessible for people with voice disorders because they are designed for healthy speech. They are designed for speech like you and I. And inherently, they're biased against non-standard speech. And when you use all these large speech models, for example, WAF2Vec, you use it for applications and different tasks, you basically perpetuate the biases. So how do we build inclusive speech models? So let's look at the problem, which is mostly healthy speech is always used for training models, which means they just cannot model non-standard speech. This is very simple. Let's create a diverse data set, and we are done with it. But in practice, this is very difficult because there is a very big variance in the human speech. And when you look at non-standard speech, every voice disorder manifests in a different way. So it's really difficult. So can we do something with data augmentation? Can we create synthetic audio? And to do this, you first need to understand how is speech produced? How do we speak and how do I make noise? A widely accepted speech production model is called the source filter model. It has two components, source and the filter. When my vocal cords flap against each other, it produces an excitation signal. And this is called pitch. When it travels through my throat and my nasal cavity, which is the filter, the signal takes shape and it comes out of my mouth. So what I want to do now is modify the source, which is pitch, and see if I can create data. This is where World Vocoder comes in. I'm going to first play an audio.
The prisoners were allowed to earn money by working in agriculture and fishing.
So World Vocoder basically decomposes audio into three components: spectral envelope, aperiodicity, and pitch. And we are looking at pitch right now, which is the bottom graph. So when I talk, right, my pitch goes up and down, it's flowery. When I sing, it goes up, etc. And this is modeled with pitch, and that is the contour that you see. So let me do a very simple operation. I'm going to say new pitch equals pitch plus 100. So how does this sound?
The prisoners were allowed to earn money by working in agriculture and fishing.
So what you basically get is, as if someone spoke with a very high pitch. And with such trick, you can basically modify the pitch contour and create data. So let me make another simple operation, which is the new pitch equals a constant, which is the mean of pitch. This is how it sounds.
The prisoners were allowed to earn money by working in agriculture and fishing.
Now, you may ask, this sounds very robotic, very unnatural. Why would you even create this data? So people with voice disorders, when they have lost their vocal cords, they use a device called electrolarynx, which is a device which basically gives one constant audio. They jam it across their throat, and then audio comes out. So I'm going to play an audio sample recorded from an electrolarynx patient.
It aggravates me. I was in the gym the other day and I was talking to somebody and there was a woman.
What you see on the left-hand side is the spectrogram of the audio that I just showed. And you see this parallel lines. This is basically, there's one constant pitch and there are overtones. And on the right side is the spectrogram of the audio that we just created. As you can see, it mimics it very well. So what you can now do is basically create any amount of electrolarynx data and improve your speech models. So I just gave a constant value, right? I can give the new constant value as 0. What does it sound like?
The prisoners were allowed to earn money by working in agriculture and fishing.
So it sounds like a whisper. It sounds like a whisper because the pitch is missing. And people without vocal cords sound like this. So with a very simple operation, you can now augment your data set with voice disorder data. So far we saw how to modify pitch, but there is a second component in the source filter model, the filter. In the case of Elena, after her initial surgery, she underwent multiple surgeries, because of which the tissue in her throat developed very differently from us. And what this means is different frequencies are given different weights, which basically translates to she speaks in a very different way. And one way we can augment our data set with this is the vocal tract length perturbation. Essentially what it does is it simulates a vocal tract and then modifies the length. And when it modifies the length, the resonant frequencies change. I will play the same audio just as a reminder.
The prisoners were allowed to earn money by working in agriculture and fishing.
When I apply vocal VTLP on this is how it sounds. Oh, sorry.
The prisoners were allowed to earn money by working in agriculture and fishing.
So it retains a similar intonation, but it feels like multiple people spoke. So we can mimic different people now. Essentially, with these two techniques, modifying pitch, modifying filter, you can create infinite synthetic data. There is a big star next to infinite because in practice, you need to control your parameters. What you can now do is You can use this as data augmentation. You can fine-tune any model you want. But let's try something more. So on the slide, what you see is a typical architecture of a self-supervised learning model, for example, WAF2Ek. It consists of an encoder, a decoder. And the latent space is consisting of deep features which we can't really understand. And that's a problem because I don't know how to modify it. What I can now do is I can give meaning to the latent features based on the source filter model. I can say it consists of basically 3 modules. So when I speak a sentence, how are you doing today? It consists of what intonation did I speak with, the pitch. What does it actually have? I'm asking you a question, content. And finally, who is speaking? It's Akash. He has a very Indian accent. He speaks in certain frequencies. That's the speaker features. What you can now do with the world and VTLP data augmentation techniques is you can modify or train each of these individual models separately. And this is super cool because with a very simple thing like L1 loss over pitch contours, you can basically start creating prosody. Now, let's move a bit further, right? So what is the reason I made it into these three bottlenecks? Assume that, or imagine that we mask out pitch only. I think you can already guess that when pitch does not exist, this produces very like a whisper data. But what if I mask out both pitch and speaker characteristics and only let content features to recreate a speech? Here's an example of audio that my colleague recorded.
Speech technology from WISP converts whisper and vocal cord impaired speech into a person's natural voice.
And when I use only the content, this is how it sounds like.
Speech technology from WISP converts whisper and vocal cord impaired speech into a person's natural voice.
So what you heard is the pitch has been removed, good. The speaker characteristics, in this case, it's Tatsu who speaks with a Japanese accent. Accent is removed, his voice profile is removed, and you hear speech in different frequencies. So why is this important? We had one of our patients record audio. He lost also his vocal cords, and this is how he sounds.
When I make a phone call with my smartphone, people don't understand me. They ask if I had a party yesterday evening.
And using the same thing, mind you, we did not use this in the training data. This is how it sounds like.
Then I made a phone call with my smartphone. People don't understand me. They ask if I had a party yesterday evening.
So this is cool. This sounds really similar to the standard speech. And this is basically what we want. The content features here encode not just healthy speech, but it is encoding something beyond that. And what we can do now is we can define properties for these content features. Maybe you have extra data from people with voice disorders. You can apply language modeling to further improve. The key thing is you can train this separately. Now, you can play a lot more with this, right? So what you can do is, let's say I have content features from the person who lost his voice, but I'm going to apply speaker features from someone with a healthy voice. What does it sound like? How do I create pitch? And what you can basically do is recreate someone's voice. We recorded a video with one of the patients, George. He lost his voice because of vocal cord paralysis. It's a condition where suddenly, due to some neurological issues, the vocal cord stopped working, and because of which he cannot talk like us.
Hello, my name is George Coster. 3 years ago, I suddenly noticed that I couldn't speak any voice, and they found out that my vocal cords were paralyzed. Since then, I speak like this. Welcome, George, here at WISP. Today you will hear your voice again, your healthy voice, and you will hear it in a second.
Hello, my name is George Coster. 3 years ago, I suddenly noticed that I couldn't speak any voice, and they found out that my vocal cords were paralyzed. Since then, I speak like this.
It's amazing. It's amazing. I never had heard my own voice, and this is very understandable. It sounds like a natural voice.
So as you can see that it creates a lot of impact in someone's lives. Communication is super important for us. It's one of the innate things that makes us humans, right? We are very social beings. And we see that people with voice disorders, because they don't communicate so much, they tend to show larger rates of depression. They are quite a lot of times lonely. And this creates a lot of impact in their lives. In this case, what we did was, fortunately, we had some recordings of George before he lost his voice. From there, we derived speaker features and applied it to his current voice. And what he can now do is basically speak to someone with his phone in front of him, or make phone calls, video calls, where he speaks the way he speaks, and on the other side, people hear an intelligible speech. In the case of Elena, though, we are still working on this challenge. Because she underwent multiple surgeries, her vocal tract is very different, and because of which we need to make our models more expressive, more inclusive. And stay tuned, that is what we are going to be working on in the near future. Thank you.
So let's go for the Q&A. Please, have a seat. Let me sit here. So if you have any question, don't forget to post it. I will be paying attention. So the first question I have here is, how long does it take to generate the voice? Is it real time?
Yeah. So one of the important things that we want is it has to be real time, because let's say we have a conversation like this. If the time it takes from my mouth to your ear is more than 40 milliseconds, as a human, you're like, something is up with this.
Yeah.
And which means we have 40 milliseconds to process audio. And we build our models like this. So we have 20 milliseconds of audio chunks at a time, and we process in less than 10 milliseconds. So it reaches the person.
Okay. Yeah. And how did you identify and separate the latent features?
Yeah.
How did you go?
So this is a bit of research. Also, there is some research going on in how to make interpretable latent features. But also, in our case, we really based it on the source filter speech production model, and it also is about the application. In this case, we wanted it to be expressive against different voice. So that means we need to remove that variance. Mm-hmm. And in the end, what happens is the common features is the content.
Okay.
With the other bottlenecks, we wanted to see what are features which depend on time, what are features which are constant in time. So no matter what language I speak, where I speak, I will speak with this kind of voice. This is a speaker feature, which does not depend on time. But I can certainly start singing to you right now. Yeah. And that is time-dependent features.
Okay. And someone asked, what are the approaches you are exploring to solve the Elena's case?
Yeah. So with Elena's case, we are actually back to the roots. We are looking at which frequencies are being tended to by the model. So what can happen in open source models which are trained on healthy speech? You can actually follow the weights, and it always follows the pitch. And what we are trying to do is simulate Elena's voice by basically doing voice conversion. So we can actually generate more data from her.
Okay.
Yeah.
One last question that I have here for now. Does it work for other languages at the moment?
Yeah. So the beauty of this is the content features that you saw is still deep features.
Okay.
It's while you use text laws or phoneme laws, there is no constraint on what language you want to train it on, and what that basically means is it can work for all languages. Currently, we do see that for Western European languages, English, and I tried a bunch of Indian languages. I know it works really well. However, again, a big star is sometimes the data that you use does not have certain things. So, for example, in my mother tongue, there are certain phonemes which don't actually pop up in any of the Western European languages. And we actually saw that these phonemes don't, our model starts to hallucinate. So you need to have a better way to represent your latent features.